In this video, we're going to learn how to solve a projectile problem where an object is launched at some angle off the ground and it's going to land back on the ground somewhere. So we can call this angle theta, and we can call this velocity v naught, the initial velocity, and we know it's going to fly somewhere and then land. It's going to move in a parabolic trajectory, and just like the horizontally launched object, whatever Vx it has at the beginning, it's going to continue to have that same Vx throughout. So throughout its flight, Vx is constant. And the Vy, whatever vertical velocity it has at the beginning, will change, but it will change by a predictable amount. It'll be a little bit less here, it'll be 0 here, it'll be negative here. And so you see that as it flies, the horizontal velocity stays constant, the vertical velocity is constantly changing. Now, what makes this a little bit difficult is often we know the launch velocity here, and we need to split that up into x and y. So if I think of a triangle, this is like what we did in our force vectors. The horizontal part, if this is v naught, Vx will be the initial velocity times the cosine of the angle. And if I think of this side of the triangle, v naught y will be v naught times the sine of the angle. I don't bother writing a naught for Vx because it's not changing. I write a naught, or the 0, for v naught y because it is changing. This is the initial velocity in the y direction, but it will change throughout the flight. So let's put some numbers in here. If I launch an object at 100 meters per second, so v naught is 100 meters per second, then what will these be? Well, actually I need an angle, don't I? If theta is 50 degrees, then 100 times the sine of 50. Sine of 50 is 0.77, so 100 times 0.77 is 77 meters per second. And the horizontal component, 100 times the sine, oops, I made a mistake here. No, I didn't. This is 100 times the cosine of 50. The cosine of 50 is 0.64. So I'm going to get 64 meters per second. Notice that the velocity, because the angle is greater than 45, the velocity in the y direction, the 77, is greater than the velocity in the x direction, the 64. If it was shot at exactly 45 degrees, we would have an isosceles triangle and we would have an equal amount. If it was lower than 45, we would have more horizontal velocity. Now I'm going to solve this the same way I did the last problem. I'm going to split it up into x and y, and I'm going to say in the x direction, how far it goes is equal to Vx times t. And in the y direction, I'm going to say that y, how high it is, depends on how high it begins, and the velocity component, and the acceleration component. Okay? If I write in, once again, if I'm trying to find how far this thing goes, some horizontal distance, often called the range, I'm going to need to find my y stuff first. So, what height does it end with? Well, I'm interested in where it lands, so it will end up on the ground. Where does it start? I'm assuming that it's launched from the ground, so v naught, or y naught is 0. And it begins now. Notice I'm not going to put my 100 in for Vx or for Vy. I've solved for my horizontal and vertical components, so I will put those in for V naught y and V naught x. Now I'm looking for a time here. And once again I have, because A, the acceleration, is negative 9.8, I kind of do this shortcut. Half of 9.8 is 4.9, so I just write that up. Now I can solve for t. This looks a little complicated, but because there aren't any terms without a t, I realize that t is going to drop out. So I'm going to subtract 77t from both sides. And now I can divide both sides by negative t to cancel the negative sign and to remove a t from both sides. So I have 77 equals 4.9 t. So how long does it take for it to leave the ground, accelerate, and come back to the ground? 77 divided by 4.9, that's 15.7. So it's about 16 seconds, if I stick with sig figs. So after launching this thing, 16 seconds later, it lands here. Now that's not surprising. Since I started with 77, if gravity takes away 9.8 meters per second every second for this object launched up, it should take about 7.7 seconds, a little bit more, for it to reach the top. And it should take the same amount of time to go from the top back to the bottom. So not surprising that it's about double 7.7, 16 seconds. Now that I know the time that it takes for it to fly, the hang time as it were, now I'm careful to put my Vx 64 in for that. I now know that the time is 16 seconds. And so what is x 64 times 16? It's about 1,024. Or about 1,000 meters. Once again, we have a constant horizontal velocity, which enables us to use a simple equation for the horizontal motion. We have a changing vertical velocity. We use our accelerated motion kinematics equation. Since we know the acceleration is 9.8 downward, and since it starts and ends on the ground, this is a fairly simple problem to solve.